That's okay, right? Is equal to C2. That's clearly 25. Okay, so you get x squared plus y squared is equal to 25. Okay? Now, this is where you have to be careful over here. Okay? X squared plus y squared equals 25 is a circle in the xy plane, right? Radius 5, obviously. Right? Okay. But the question is, we want to get, is there a solution unique? And if you look at your existence uniqueness theorem, you'll find that the solution is unique, provided that y is not equal to 0. And we're looking for a solution that goes through 4, negative 3. Let's take that out, okay? We want a solution that goes through 4, comma, negative 3. Remember, this is 5, 0, it's right on the circle, right? Okay. So, when you solve for y in terms of x now, normally you would have y equals plus or minus the square root of 25 minus x squared. Okay. But our solution basically has to yield the value of negative 3 when y is equal to 4. And I think you can see in that case, you have to take the negative square root minus the square root of 25 minus x squared, right? Because you plug in x is equal to 4, square root of 25 minus 16, 9, which is minus 3, okay? So what happens in this case is the actual solution to the differential equation is right over here. And we put a little circle over there to eliminate that point because it's not defined, okay? So solution to this differential equation satisfying those initial conditions is the lower portion of the circle, but excluding the points 5, 0, and negative 5, 0. Why did I exclude those points? Because y goes to 0 there, and it's not even defined, be an infinite slope. Of course, had my initial condition been let it go through the point x equals 4, y equals 3, I'd get the upper portion of the circle. Okay? So it's right, this happens a lot of times when you go and you integrate, you see you get this, and then people make the mistake of stopping at this point. Okay? But wait a minute. Okay, this is what's called a multi-value function, right? You get two branches of the square root, and you have to look back at the initial condition to know which one they need to take. Okay? Okay, now this one is going to be like a little more interesting. And again, I'm going to be doing some techniques in integration, things like integration by parts, partial fractions. I assumed you had that in calculus. Again, I understand some people it's been a long time, a little rusty, and I'm glad to help you on that, but I can't take class time to do that. Right? Okay. Just need to draw it out. So a third example. These are all separable. Let's look at the equation dy dx equals y squared minus 4. Okay? And I want you to get an analytical solution for that. Okay? What's interesting also is that we're going to revisit, after we get the analytical solution, we're going to look at it. It's also an autonomous equation, right? Because the right hand side is only a function of y. And we'll see that the two agree perfectly with each other as far as qualitative behavior becomes. Okay. So what I'm going to do now is divide through by y squared minus 4 to make it separable, right? So I got dy over y squared minus 4 equals dx, right? Now, if someone's careful, right at this point, you say, whoa, wait a minute. What happens if y squared minus 4 is equal to 0? Can't divide by 0, okay? And matter of fact, that's very important. This assumes y not equal to plus or minus 2. Okay? Now, what happens, y equal plus or minus 2 are solutions. If we would have done it with the autonomous thing, it's the first thing we would have done, right? So basically, you do have these solutions. So note, y equals 2 and y equals minus 2 are both solutions. Okay. But there are other solutions to the equation. When y squared minus 4 is not equal to 0, and then we can get those y as a function of x. And then we're going to go and see, are these two solutions, y equals 2 and y equals minus 2, are they contained in the general solution we're going to get subsequently? You'll find out that one will be and one will not be. Okay? So when one asks for the complete solution, you have to be careful. Okay? You do this thing first, you divide through y squared minus 4, you make a note, wait a minute, I got these two solutions, and then it may happen that when you get the general solution, you've ruled those out, or they may be included. Okay, just have varies from problem to problem. Okay, so now, of course, here's our problem, basically. Right-hand side is easy, right? Integral dx is just x plus constant, right? But what do you have on the left? 1 over y squared minus 4, and you have to remember partial fraction expansion, okay? So, 1 over y squared minus 4, okay? You can factor that into 1 over y minus 2 parentheses y plus 2. And if you look back in your calculus book, these are what's called simple roots. That's going to be some constant, what's called a1 over y minus 2, plus another constant, a sub 2 over y plus 2. In other words, there will exist numbers, a1 and a2, so that 1 over y minus 2 y plus 2 can be written as something over y minus 2 or something over y plus 2. Now, how do we get a1 and a2? There are two ways. What you can do is multiply through by y squared minus 4 and just match the coefficients. Or you can just do a little trick, which, I'll show you, that is a little faster. What I'm going to do now to get the a1, here's what I'm going to do. I'm going to multiply both sides of this equation by y minus 2 and take the limit as y approaches 2. When I multiply by y minus 2, this cancels, right? When I multiply this guy by y minus 2, I land up with a y minus 2 in the numerator. When I take the limit as y goes to 2, it's 0. See, it goes away. Okay? So therefore, a sub 1 is just the limit as y approaches 2. Again, it's multiplied by y minus 2. That gives me a1. Multiply by y minus 2, that goes out. What happens over here when I multiply by y minus 2? I get 1 over y plus 2. Okay? And that comes out to be a quarter. Another way you can do it is you can expand, like I said. Just multiply through by y squared minus 4 and match all the coefficients on the left and the right. Okay? A sub 2, we can do it a similar way. To get a sub 2, I'm going to multiply both sides by y plus 2, and then let y go to negative 2, so this guy will go out. So a sub 2 now is just a limit. As y approaches negative 2, I multiply by y plus 2, I get 1 over y minus 2, and that becomes negative a quarter. Okay. So what we've shown is that 1 over y squared minus 4 is equal to, let's factor out, a quarter. A1 is 1. 1 over y minus 2, right? Minus 1 over y plus 2. Okay. See, so now I can go back and do the integration. So now we're back over here. Okay. So, on the left-hand side, I have the integral dy, 1 over y squared minus 4, which really comes out to be the 1/4, the integral of, I said what, 1 over y minus 2 minus 1 over y plus 2 dy is equal to, on the right-hand side, x plus an arbitrary constant. Right? That one's easy. Okay, this is multiplied through by 4. What's the integral of 1 over y minus 2? Let's assume y is bigger than 2 for the time being. That's the log of y minus 2 minus the log of y plus 2. I would ln and log, they're the same, right? Log y minus 2 log plus 2 equals 4x, let's call that, plus let's call it C2 instead of 4C1. Okay? So now, you use the same, again, you have to know your log business, right? Y minus 2 over y plus 2 is equal to 4x plus C2. Okay? So far, so good. And again, we want to get y, so if the logarithm, by definition, of a quantity is equal to 4x plus C2, by definition, the thing you're taking the log of, in this case, y minus 2 y plus 2, is the exponential of 4x plus C2. Okay? Now, again, rules of exponents. I expect you to recall that e to the a plus b is e to the a times e to the b. And again, every term someone screws up on exams because they don't remember the laws of exponents. Okay? So, E to the 4x plus C2 is what? It's E to the 4x times E to the C2. A lot of people put plus, and they get the whole thing wrong, okay? E to the C2, let's just call that C3, right? So some arbitrary constant exponential of 4x, okay? And the rest is just algebra. I won't go bother to do it. You know, you multiply by y, you want to solve for y. So multiply by y plus 2 and bring it to the other side. You can easily solve for y in terms of x. Okay, let me just give you what that result is. When you solve for y in terms of x, you should find y equals 2. And then I got 1 plus an arbitrary constant. I don't know if it's C3 or 2C3, you know, depends on the algebra. But yet 1 plus a constant e to the 4x divided by 1 minus that constant e to the 4x. Okay, that's the solution. And there's a 2 in front. Okay. Now, that looks like the general solution. It's got one arbitrary constant. But remember, we divided through by y squared minus 4, and we may lose one of these two guys, y equals 2, y equals minus 2. Let's see. What happens over here now as when x goes to negative infinity? Okay, I want to get y equals 2. Okay, let's see if I can get y equals 2 over here by choosing c somehow. Yeah. Suppose I choose c equal to 0. Just plug in c. Remember, c here is an arbitrary constant, right? And the question is, you know, does this more general solution actually absorb these two? Is it contained enough? If you put c equal to 0, you get y equals 2, right? Good. But there's no way you get y equals minus 2. You see that? There's no way getting y equals minus 2 over there. If you want to see formula, just put equals minus 2, try yourself a c. There's no constant value c that'll give you y equals minus 2. So the solution to the problem, y dx equals y squared minus 4, is this, and y equals negative 2. Okay? Now, what's interesting about this also is this. I'm going to show you a graph of this with different values of c. And then we're going to go back and do the old autonomous result, and I'll show you that it probably wasn't even necessary to look at the computer for this, but let's do it anyway. Okay? So, make sure I have this thing graphed. This was a separable equation. Let's see if I can show plots. No, it's the next one that I want to show, so it's not even the computer at this point. Okay. But let's just quickly, let's look at the equilibrium over here, right? dy dx equals y squared minus 4 is autonomous, right? So if we were doing it the old way, the qualitative way, we can get y equals to 2, right? And you get y equal to minus 2. Okay? And then you can then look at all the regions, right? What happens when y is bigger than 2? Then dy dx is positive. So one solution would look like this, right? And then you got a solution in between plus 2 and minus 2. Okay, the slope is negative, so it's going to fall to the right. So goes like this. Over here's going to go like that, right? Asymptote. And similarly, you can do one, you know, down here, right? It's going to be also happen over here when y is less than minus 2. It's like still positive, so it's going to go like that, right? And believe me, if you take values of c and plot this up, you would see exactly like that, okay? Over here, it's not apparent that you get those type of curves, right? So it's interesting that, again, you have the analytical solution. You know, sometimes it's good to do that also. Get a little more insight. Okay, now the next one is very interesting. The solution is going to be very complicated, okay? But the reason I'm doing this is because Again, to show you how implicit solutions come up quite often in practice. Okay? The integration won't be hard at all to do. It's just that when you look at it, we're not going to be able to solve y in terms of x. So that's where you have to, kind of supplement this with some computer plot to see what's going on. This is example number 4. Okay? Okay, here's the differential equation. dy dx equals e to the y times the sine of 2x divided by the cosine of x, e to the 2y take away 1. E to the 2y take away 1. And let's make it into an initial value problem, y of 0 equals 0. Okay? So I want a solution of the differential equation where the slope dy dx is e to the y times the sine of 2x. Downstairs we have the cosine of x, parentheses e to the 2y take away y, and it should go through the origin. Okay? If you look at that, it is separable, right? dy dx is a function of x times a function of y. The function of x is sine 2x over cos x, and the function of y is e to y over e to 2y take away 1. Okay? So, let's get rid of this thing by multiplying, I guess, by the reciprocal. So I have e to the 2y minus y divided by e to the y, right? That's my differential of y, right? E to the 2y minus y over e to the y dy. And on the right-hand side, it looks like I'm going to have sine of 2x divided by the cosine of x dx. Okay? Clearly what you want to do is do the long division on the left. So basically you have e to the y minus y e to the minus y, right? Differential of y. E to the y minus y e to the minus y dy. And remember the formula for sine 2x is 2 sine cosine. So we get 2 sine of x dx. That's the easiest way to do that. Get rid of that sine 2x, the double angle formula. Okay. The integral of 2 sine x is easy. That's just minus 2 cosine x. And we have to work on the left-hand side a little. Okay? The integral of e to the y, that's easy. So let's integrate. On the left-hand side, what? I get e to the y minus the integral of y e to the minus y dy. Remember I said I'm not going to expect you to know really crazy integrals, but this one is integrated